all three CAN generation will still be alive.
Yes.
Classical CAN will be used for a long time.
Everything is possible with CAN, and I think that architectural flexibility is also really beneficial, at least speaking for the CAN technology.
Because at the end of the day, the CAN bus is a hidden thing in the car. You don't see it as a kind of competitive advantage to have a CAN bus. No, everybody uses this, it has to be invisible.
Hello everybody, my name is Mike van Haren. I'm Product Marketing Manager at NXP's in-vehicle networking for CAN products. And today we're going to talk about CAN. Today I have with me Holger Zeltwanger, who is the Managing Director of the CiA, CAN in Automation, which is a non-profit organization talking a lot about CAN topics these days, of course. And also I have Matthias Muth with me, who is a Senior Director of our Systems and Applications team within NXP. Both are very principled and know a lot about CAN, and today we're going to have a good discussion on what has CAN done in the past and where will we move into the future. So we have received as NXP this sign of a 30 years cooperation between NXP and the CiA. And maybe to start with, I'd like Holger to discuss a bit on CiA 30 years. How was the party, 1st and 2nd of June?
It was a good party, and there was a lot of people there. I think that it was unexpected that we will have such a long lifetime, because when CAN was introduced in the mid of 80s and developed by Bosch, and then we was not thinking that this technology will be so long be used in cars. However, when we had in 2012 the second generation, I was surprised on that because I have not expected it. But 6 years later, in 2018, we started already the development of the third generation. And this shows that CAN will be maybe still available in the next decade or the 2 decades. This will be maybe after my lifetime.
Very good. Yeah, happy to hear that. Maybe to start also with a bit of, let's say, looking forward. So we see now the OEMs, the car manufacturers, at the decision phase to select which technology they're gonna use. So we see typically the architectures changing from a flat architecture into domain controllers or domain controlled architectures, into zonal architectures. CAN, of course, is being pushed a bit to the edges of these architectures. The central brains, the zonal controllers are typically dominated by the Ethernet for the high bandwidth. Of course, we don't talk about CAN speeds anymore. We talk about gigabits, which is, at least today, still not possible with CAN. We still expect that CAN will have a very significant role to play in the future in domains, up to, of course, the OEMs to decide which way to go. Maybe Matthias, can you tell a bit about what kind of decision criteria there should be considered?
CAN is typically used at the last meter, so to say, so collecting information, sensor information, this kind of stuff, or driving actuators on the last meter of cable, where at the end the protocol property is not the thing which is important, it's the flexibility you need. So the CAN bus is an excellent example where you can put nodes to such a bus without the other nodes to know about it. That's one of the, let's say, properties of CAN, that there's a bus access mechanism which you do not need to know if there's a new function coming in. So the competitive technology, which is 10-base T1S in that case, which is also aiming for the same, let's say, speed domain, they need to know on beforehand who is there, because it's a kind of slot-based bus access mechanism. So they have different flavors. So the 10-base has a flavor of this IP communication, while CAN has the flavor of just plug and play. And therefore, I believe as well, both technologies make sense. But CAN, to my opinion, will not disappear, because it has special properties which are very, very useful for these last meters.
maybe the last meters is sometimes 100 meters ago. Also, CAN is capable to run up to 1 kilometer, and we have CAN, for example, on the ocean ground or in huge machineries, lift applications, or for those speaking American English, this is then elevators. So this is the same. We need the last meter, but means the front end.
Yeah.
The front end could be sometimes very long distances.
And yeah, right now we are also talking about container ships, by the way. So that was one of the last things which happened also during the CiA event, by the way. So where people from the, let's say, marine application said, hey, look, we have container boats. They are also using CAN. We have 500 meters of cable here from the, let's say, captain down to the machine room somewhere. So also that's an interesting aspect of the CAN bus.
Yeah, let's come back to the history maybe, that we see how this all works and what is the cooperation between CiA and NXP. CiA was established in 1992, so 30 years ago. This is why we have had this year the anniversary. And from the beginning, NXP was participating in the meetings. And this was very important because of two reasons. The first reason, after 2 months, we agreed already in the CiA membership on a connector pin assignment. This is still valid today. This was the base, so to say, that you can connect things together. The second is, or was, that we need a transceiver chip, because in the beginning there was no transceiver chip available. The specification was available, but no product. And we received from NXP predecessors the chips, and we showed in the first Plugfest on a fairground that 23 companies could communicate with their products. And this was one of the first things which we have done. And I think still today, and coming back to the fast development in the last years, we have had Plugfest in 2012, as well as in 2020 with the CAN XL and CAN FD technologies.
Yeah, so I just looked a little bit into my old history, and you can still find the famous 82C 250 transceiver. You remember that was the first device. It was somewhere early 90s, I think. And the funny thing is, this device is still in mass production. So we are talking about 30 years of mass production of the first CAN transceiver, and there's no end in sight, I would say. Yeah. So this data sheet was, or this is a nice announcement with top EMC performance. So nobody knows EMC at that time, so it was quite new stuff, I would say. And so today, of course, everybody knows what it is. But at that time, no clue what you need. But still in production, so it's really funny.
And then, of course, we also had quite swiftly after that the introduction of the PCA 82C250, which was the first integrated CAN transceiver, I guess. So yeah, I think also for that we are still producing that one, also showing the old stuff is still not gone and is still very relevant today. But of course, there's new developments ongoing. Right.
Yeah, so that was the first transceiver, but there was also a CAN controller, of course, available at that time. So the very first standalone CAN device, the C200, not existing today anymore, but there was a predecessor, so the SJ1000. You might know it because we received a nice CiA award at that time for this development. So yeah. It's another nice thing from history. So I just looked it up. It's from 1997.
Yeah, it was given during the International CAN Conference. Yeah. Which we have had always, we have had 17 different international CAN conferences, always with participation of NXP, with good speeches, and some of them are also on YouTube, and you can watch them. Yeah.
It was actually the first CAN controller where you also had good diagnostics capability, so that was a unique point at that time. So in history, people did not know why the CAN bus was not working. They just looked to the signal, and strange enough, it is not working. But this was the first device giving you insights what exactly the bit problem was to really debug then systems as well. And this is still used. So even that device still in production today.
But most of the products today used for CAN communication are integrated in a microcontroller. This is the state of the art, but exception for the tools and for all other things which we need to test and to verify things.
If you need an extra channel somewhere and it is not there, yeah, still these old controllers are coming up.
And then of course we had the first technology there, and then the big journey started I think there was a scream for higher bandwidth, there was a scream for a more optimized technology, better interoperability, EMC performance, ESD performance. So over the years there was a lot of cooperation between NXP and CiA, also in the standardization side of things. So typically what we have seen and what is still being done is that we do a kind of a pre-standardization in the whole community of CiA. After that, bring that to official standardization groups, where we then have typically the full global acceptance of things. So we have been deeply involved as NXP, always in the standardization settings and definitions. So it all started with the first technology, single wire CAN. We had, of course, high-speed CAN, fault-tolerant CAN. And then really we went into today's technologies, CAN-FD, CAN-SIC, now CAN-XL is on the table. Can you maybe walk us through a bit on a standardization process? So you see a request coming from the market, you see a gap somewhere, and whatever happens, and then you jump in.
Yeah, if you look back to the 1993 when the first ISO 11888 standard was published, this was done, let's say, in those old days, more or less it was something written down. Today we are more serious and we try to write the standards in the right way so that even foreigners or non-native speakers can understand them, and we use an improved format to describe those standards today. When I jumped into that was end of the 90s. I was becoming the chairperson of the working group responsible for the entire series. In the meantime, I'm responsible for all in-vehicle networks. And we have rewritten the standard in 2003. We split it into the data link layer and in the physical layer so that different implementers or different readers can now better understand the standards. With the support, and sometimes NXP engineers were leading this, they were the project leaders for several of the physical layer standards which we have had. In the last revision in 2015 time, we combined again some of the splitted transceiver chips, so that all what is related to the high-speed transceivers, what is well known under ISO 11888-2, is now into one document again. So that we have had the problem that we have had used different terminology in different documents, and this was confusing. This has been all finished now. We are updating it, and now we are looking for the next generation already. This is not more CAN-FD and its improved capability of transmitting data. Now we are looking to CAN-XL, and there we also have a new physical layer specified. It's called CAN-SIC-XL transceivers. This was done under the umbrella of CiA. And before we had a similar approach for the CAN-FD technology. Also there we are using the SIC transceiver, mainly developed with the help of NXP and their engineers, and we have done a lot of plug fests for that purpose. And there we proved that not just a theory is in the paper, but also that we can practice it.
Exactly, it was a really great success to do that under the hood of CiA, to be honest, because it was really a very powerful team, so to say. We were really effective all together. It was very fast. It was incredibly fast, so to say. If you compare it with ISO standardization, we did it in more or less 2 years, I would say, from the first scratch down to the final document, which was really impressive, at least to me, because I know how it worked in ISO before. Usually every half a year you make a small baby step somehow. And here it was really within 2 years from the beginning to the end. And we did the same with CAN-XL. Again, in CiA with a very successful plugfest at the end. Very nice.
Yeah. And I think that's also one of the big advantages for NXP, that we are in close cooperation with CiA. So we have also seen that the first CAN SIG transceivers for TJ1462 and 1463 have been released to the market already a few years ago, 2019 by heart, where we really now see also that the technology develops also towards CAN XL, where you say on the physical layer we now use CAN SIG XL. I think that has been very, very powerful, at least also from our side.
Maybe a point from my side. I was not surprised because we are all developing CAN technology, and CAN communication technology is by its definition democratic. So everybody has the same right, nobody is ahead of the others. We design something and we behave in the CAN or the CiA community in the same manner. This is important, that we respect each other and that we do it together, jointly. And this is unusual in the industry, and sometimes people think this is not possible, that even OEMs bring their knowledge into, or their experience into the CiA working groups or into the Plugfest, and then we learn all together.
There's no real secrets anymore, because at the end of the day the CAN bus is a hidden thing in the car. You don't see it as a kind of competitive advantage to have a CAN bus. No, everybody uses it. It has to be invisible. As long as it is invisible, we did our job correct. If it gets visible, we have a problem, I would say.
Maybe this is like in human communication. If we use the English language, this doesn't mean what we are talking. It's just we're using the language. And this is like a CAN communication. We're using this on a technical base, not as a human base for communication. And I think this is one of the important things which we should continue to do.
Absolutely.
Yeah, so then looking at the future of what we have as CAN today. So we see nowadays CAN signal improvement is able to drive really the CAN bandwidth up to 2 and 5 megabits. We see the adoption also coming from the OEMs, from the car makers. They need to have this bandwidth to support their higher data rates, data packages that they want to send. Next step after this will be, of course, CAN XL. CAN XL will be 10 megabit typically, but we already proven through our L by 20 concept that we have a possibility to even move up to 20 megabit per second. This is going to be, let's say, the threshold where a OEM needs to decide whether to use 10BASE-T1 on the Ethernet side, having everything IP based up to the edges, or going for a CAN-based solution, which is then going to be probably CAN XL, which is of course beneficial in the sense that we have already a lot of persistent nodes in the market available, ECUs which carry CAN technology. You don't want to have your whole system maybe redeveloped, and with that it's very convenient, of course, to use the CAN protocol still. Then there's also something coming up like a CAN to Ethernet translator, moving the CAN-based communication towards a time-synchronized network. How do you look at this for the future?
First, I would like to make a statement that all three CAN generations will still be alive.
Yes.
Classical CAN will be used for a long, long time. I give you just an example. Last week I was in Austria and I talked to somebody who makes dentist chairs, and they use internally in the dentist chairs, they use a CAN network. They don't have a speed issue because they don't want to move their patients quicker. This is still the same with the seats in the car. And other applications, of course, we need CAN-FD, not only because of the speed, we need it also because of the payload. Because if you want to protect things with functional safety or cybersecurity, you can't do this with 8 bytes of data per frame. Then you need a minimum 64 bytes per frame. If you want to go a step further and you want to integrate the cybersecurity in the data link layer, of course, this maybe is only possible with CAN XL, and we are working on this. We have the CAN SEC protocol under development, and this is maybe the future for those applications. So I think that all three generations will have their markets in the future for the next 10 to 20 years. And of course, depending on your application, and Matthias had said this very right, we have the scalability of the physical layer and the scalability of the data link layer. Yep. This is unusual. There is no other bus system which can go for such small applications up to the bigger ones.
Yeah, that was actually one of our big challenges with CiA and NXP, to make sure that even this complete new physical layer somehow integrates into the old world. And that took a while to find the trick, but finally we made it happen, so that's a good thing. We could demonstrate today, in principle you can put whatever you want on the same piece of wire, whether it's the very old CAN thing or the new CiA and NXP, it works. That's the good thing. And just want to mention something about the payload. It's all about also over-the-air update, which is coming into more or less all modules in cars. That means if you want to download software into a node and you try that with 8-byte messages, of course this would be kind of a mess, but it is done today, but it's damn slow. So therefore you need these long payloads. Whether you at the end of the day need the full 20 megabit is a different story, but I would say 10 megabit with, let's say, 2048 data bytes is already a massive difference. And software update is the topic of the future, like today. And software is that complex, meanwhile, that the download files are so big, you need that speed. Otherwise, you have no chance for in the field updates.
Yeah, and CiA and NXP has in addition some new features, also like Ethernet, to support higher layer protocols by definition. So this means we have, like the Ether type, we have the SDT type field where we can distinguish between different applications. Mm-hmm. And this is important because nobody will change the entire car in one shot. So this means we need a migration path, and the migration path is available for CiA and NXP. So you can use the classical CAN, you can use CAN FD, and all the different proprietary and standardized higher layer protocols. Mm-hmm. You should know that, for example, not in the non-automotive industry, there is a lot of higher layer protocols standardized, also in commercial vehicles. So they have been standardized their things. In passenger cars, it's just the diagnostics which has been standardized, to be honest. All others is more or less OEM specific, but we need this migration path for all the different application fields.
Yeah. And of course, we know that CAN has a big flexibility in what topologies you want to apply. Is it a daisy chain? Is it a bus stub node topology? Is it a star topology? Everything is possible with CAN. And I think that architectural flexibility is also really beneficial, at least speaking for the CAN technology.
Yeah, it's also for car manufacturing a huge, massive issue, sometimes underestimated. Think about the daisy chain, which only works if all nodes are populated. Yeah, you have to connect from one to the next to the next. And if you build your car, first step, this module built in. But the others are not there yet, so you can't test. Next module built in, you still can't test. You need to wait until the full population is there. And then you need to test suddenly 5, 6, 7 mounted modules. That's not practical for automotive use cases. Therefore, you need always to test what you have built in. Otherwise, you can't fix it in the production line immediately. Otherwise, you get a car at the end, oh, damn, it's not working. Yeah, if I would have known that this module has a problem, I could have fixed that immediately. Now you have to do it end of the line, and that's something which is one of the drawbacks of this daisy chaining. So for industrial, not that much of a problem, but for automotive, in principle, a big mass production problem. So they need topologies where you can plug nodes, and from that moment onwards you can test. So that means star topologies, or at least stub topologies, where already 2 modules can talk to each other without the others even being populated.
But on the other hand, if we have this scalability and the different choices for different topology, this means you have to have knowledge on the physical communication. This is not more that easy as with classical CAN. CAN FD and CiA and NXP are challenging. You should know a little bit more. Yeah. This is, of course, if you want to have flexibility and scalability, then you also need some knowledge.
You need to know what you're doing. Yeah.
Yeah. And CiA provides for that purpose recommendations, so that we don't leave the users alone. We help them with all our knowledge and the knowledge of NXP and other CiA members. We will write recommendations how to design systems and how to design products, also on the ECU level. Yeah.
And I think this is also adding up to the story that we try to support, is also to do network topology simulations for our customers. We support the OEMs with that, so that at least we know that in case an OEM starts to implement a new network topology, that it works. At which speed it works.
So simulation is then using actually the standards from CIA where the theory is explained, look, this is where you need to take care of, and the simulation is then the practical, let's say, translation of that specification into something functional.
Which in the end is really appreciated, what we recognize at the OEMs also.
Yep.
Matthias had said it already, that there are strange applications, like in maritime electronics with 500 meters. Also those people need support by our recommendations for the physical design. We have the same also on the outer space. You know that CiA is before human beings are on the Mars already, and in many satellites and unfortunately also in some military applications we are using CiA, of course, and this is one of the let's say the limits which we have to go to the outer space, but we also go under the sea. So we have also huge networks laying on the ocean ground to protect the exploring of oil and gas. And there's a lot also, they have a length of 1 kilometer. They have no speed issue, but reliability. And reliability means they need also some, and availability, they also need redundant networks, because otherwise you have to go deep into the sea, and they don't like to do that because this is too expensive and too dangerous. So they should stay there for more than 20 years.
And they use fault-tolerant CiA, I guess, partially at least.
Yeah.
So there's another flavor of the famous CiA physical layers, which is not that much used in automotive anymore, but was a very nice exercise as well, to have real, let's say, autonomous redundancy in the physical layer already by just switching to single wire operation if something goes wrong.
Maybe if we talk about a final statement, just your personal view or your personal wish, where would you expect or where would you wish CiA to be in 30 years from now? So we just celebrated 30 years of CIA. 30 years further ahead on the road.
Maybe 30 years is after my lifetime. Nevertheless, I think CiA will survive me, okay? Because there's a lot of applications just starting, and just looking to trains. They start now to use more and more CiA networks for door control, for all the things internally, and they have a lifetime of 20, 30 years. They will be still available. We have other things like the outer space. They have satellites. They will stay there for the same time frame. And we have the same also for all other conservative industries, including maritime industry, medical industry. All these things will stay for a long, long time. And I'm quite sure that CiA has still a bright future with all those three flavors.
Absolutely. So it's robust. It's proven to be robust. It's proven to be flexible. So this is the properties of CiA. You can just plug it together and it's working. Yeah. So there are hardly any problems known, so to say. So why to change a system which is great? If there is another system running on the same speed, same cost, with different flavors, like 10 base T1, okay, will also exist, but it has different fundamental properties behind. And at the end of the day, the end application will decide what is the most smart thing to use.
And maybe looking at the bandwidth that CiA is offering today and tomorrow with CiA XL, there's still a gap towards, let's say, next level Ethernet connection, which is 100 megabit. Would you expect that gap will be closed by CiA?
I would say with the current CiA XL physical layer, we really brought it to the physical limits, what you can do with simple bit coding on twisted pair under the umbrella of the EMC requirements we have. That is end of the game, I would say, for this kind of signaling. If you go for higher speeds, you are leaving the baseband, so to say, like 100 base T1 is doing. Then you need a different coding scheme. So for the bare CiA as it is, I would say CiA XL is the physical limit we have achieved now, but only from speed perspective.
Good. Then we'll leave it with this. Holger, Matthias, thank you a lot for joining this conversation. In case you are interested in following more on the future of CAN, you can subscribe on the CiA newsletter, where you get regular updates on the latest technology developments. Or otherwise you can use our website nxp.com/CAN, where you can find, of course, information on the latest products and the latest technologies. Thank you very much for watching.